Today we will be beginning chapter 2.2. So put it down over here, chapter 2.2, and that is about the thermal properties and temperature. Assalamu alaikum.
Walaikum assalam.
Just got started.
Okay.
So the first thing we're going to talk about is the thermal expansion of solids, liquids, and gases. Right, so we've talked about the kinetic particle model, and right, we've talked about how the particles are arranged in solids and liquids and gases, whether they're in contact, how close they are, their vibration, their speeds, right? And so according to the kinetic particle model, when you heat, right, there's more energy, and so, right, the particles vibrate faster, so the more vibrations, faster vibrations, and so the particles move apart, right, further apart, and that is expansion. So in solids, right, expansion is very small relatively. So in solids, linear expansion, meaning, right, change in length is relatively very small, and you would need large pieces or lengths of solids for observable expansion. It's not that it's not happening, but for you to be able to observe it, right? Take note of it. Or, right, the temperature change must be very large. So it's mentioned that for a 1 meter length of steel, right, a rise of 1 degree centigrade will, right, in temperature will cause an expansion of 0.012 millimeter, not centimeter, not meter, 0.012 millimeter. As you can see, obviously that is very small.
Yeah.
Then we come to liquids. So we know that the particles are already right further apart as compared to solids. And they are less organized, right? So they don't have a specific shape. They're not being held tightly in place. They are more mobile. And the interaction between the particles is less. And this allows for more expansion. Why? Because what is the interaction talking about? We're talking about the attractive and repulsive forces. The attractive forces which are keeping them together, the repulsive forces which are, uh, you know, overcoming compression, right? They are, right, not allowing compressibility. So when the interaction is less, when particles are not held in place tightly by the attractive forces, then when they gain energy, it's easier for them to move apart.
Okay.
Right? And so there's more expansion in liquids and it's easier and more expansion in liquids than solids. And I believe they give a ratio over here that liquids typically expand about 5 times more than solids for a given temperature range. Than solids for a given temperature range. Is it just me or I feel like my handwriting is extra good today?
Uh, Slightly better.
I was being sarcastic. I feel I'm scribbling more.
I was sarcastic as well.
Okay. I'll try to be neat.
Yeah.
Okay. Uh, right. So, for example, right, steel was expanding with a 1 degree rise. It was expanding by 0.012, and so, right, a liquid steel, for example, if you want to compare, might expand by 0.060. That's 5 times, right? Millimeters. Then you've got gases. And we know that the interactions between gases are few and the forces between them are very weak. They are very far apart. And so, right, when given energy, they move away even more quickly. And right, they're moving quickly as well. In general, move quickly. So when you're supplying energy, you're heating it up, right, they expand much more easily than liquids. And so compared to liquids, gases expand 20 times more. For a given temperature rise. Right, and so obviously expansion in gases is the highest, and so that would tell us, about expansion, that gases, liquids, solids, or that's how expansion works. Clear?
Yes.
Any questions?
No.
So now we come to uses of expansion.
Yes.
Question, Karan? So let me just share a video with you which would explain a lot. Just give me a sec.
No.
Karan, you can't see my screen?
No.
No? Okay. Let me reshare. What about now? Okay, so here we have a video that's explaining the application of thermal expansion and contraction. Right, I don't want to go through the whole thing.
Applications of thermal expansion and contraction of solids. It is a matter of common experience that a solid expands on heating and contracts on cooling. Expansion or contraction could be in length, area, or volume. We use instruments made of different kinds of solids in our daily life. Solids expand during the hot summer months and contract during the cold winter months. Expansions and contractions of solids are sometimes useful, while at times they pose many technical or engineering problems. In bullock carts, iron rings are fitted on to the wooden wheels. The radius of the iron ring is taken slightly less than that of the wooden wheel. The iron ring is heated. On heating, it expands and its radius increases, enabling it to fit onto the wooden wheel. Later on, the iron ring cools and shrinks to its original size, clamping itself firmly to the wooden wheel as shown here.
Okay, so that was
A metallic cap stuck on a glass bottle can be removed by pouring hot water over the cap. When hot water is poured over the cap, it expands due to a rise in its temperature and can be removed easily. Thermo
In fact,
switches or thermostats used in automatic switching on and off of the electric supply to any appliance use bimetallic strip. A bimetallic strip is made by riveting two metal strips, usually one of brass and the other of iron, at their ends. On heating, brass expands more than iron, hence the strip bends with brass on the outer side. These bimetallic thermoswitches are used in appliances such as automatic fire alarm systems, electric irons, ovens, etc. The use of a bimetallic switch in an electric iron and in an automatic fire alarm is shown here.
And I'll go back to the whiteboard and explain some of that. Let me just switch sharing. Okay. So in your text, the example that they've given are an axle that is shrunk by cooling and fitted onto the gear wheels. Alright, so expansion and contraction. Just a second. And contraction. Alright, so expansion is when the particles are moving further apart, and contraction is when they're moving closer. So one of the examples they've given is the axles of vehicles, axle rods, and they are shrunk or contracted by placing them in liquid nitrogen and then fitted onto the gears. Right, and when these axles later expand and come back to room temperature, expand. What's going on? Room
Can you please explain the use expansion again?
temperature, and so they fit tightly. Right, the other example given, the video was of an iron ring, so that's the opposite, iron ring on a wooden wheel. And so in that case, the iron ring was expanded, fit onto the wooden wheel, and then when it came back to regular temperature, which was cooler, it contracted and fit tightly onto the wooden wheel, right? So you wouldn't be able to remove it just like that. Right, you saw the example of removing metal lids of jars and cans and bottles. Right, you can do that. And the whole working of a thermometer, whether it's a whether it's a liquid mercury or an alcohol thermometer. Both work by taking in heat of whatever you're measuring and expanding and then telling you how hot or cold something is. Then is the bimetallic strip. So the way bimetallic strip works, basic concept is expansion, but what they do is two different metals are joined together. Right, so they're riveted together. So like joined, not like with tape or glue. They're riveted together, and so they can't move separately. And so when they're heated, for example, the example in the video was brass and iron. The one in your book is for copper and iron. And so what happens is that they have different rates of expansion. So it's not just gases expand more than liquids and liquids more than solids, right? Even among solids or even among liquids, right? Different liquids or different solids expand differently for the same rise in temperature. And so copper and iron are both metals, but their rate of expansion for a certain temperature rise is different.
Okay.
Right? And copper expands more than iron. So what happens?
Can you please explain that again?
So even though copper and iron are both solids and they're both metals, right? But for a certain rise in temperature, copper will expand more than iron, right? Why? Because the particles are easily moving further apart as compared to the particles in iron for the same temperature rise, right? So for example, the temperature rises by 10 degrees centigrade, right? And these were the particles of the metal, right? Both iron and copper. So after 10 degrees rise, copper is like, for example, this, and iron is this. So they've both expanded, but copper has expanded far more than iron. Is that making sense?
Yeah.
Aram?
Wow.
Aram, is that clear, or do you need further explanation?
Can you please explain it further?
Explaining it further. Okay. So if I just take you over here. For example, you've got a strip of iron and a strip of copper. Well, actually, this is the red one's copper and the black one's iron, right? And you provide heat to both of them. And so the temperature will increase and they will expand. Both of them expanding. But, right, so this is copper. This is iron. What you will notice, for example, if you raise the temperature, for example, from 30 degrees centigrade to 50 degrees centigrade. That's a 20 degrees rise in temperature. What you will notice is, let's say both of these strips are 10 centimeters. After heating, you will notice that the copper strip, for example, right, is now 13 centimeters, for example, whereas the iron strip is 11.5 centimeters. So they've both expanded. Expansion has occurred. But copper has expanded more than iron. Why? Because even in different solids, how much they expand is it's not the same for all solids, right? So you take iron, you take zinc, you take aluminum, you take gold, you take a rock, right? You take any other solid that can be heated to expand, and right, they're not all the same. Right, how much they expand for a certain rise in temperature, for a given rise in temperature, is different. And that all depends on, for that particular solid, what kind of interactions and how strong the interactions between their particles is. Any better?
Yeah.
Okay, now exactly what happens over here in a bimetallic strip. You've got the copper and you've got the iron. Right, and they are riveted together. When they are heated, so when you provide heat, so this is a bimetallic, bi meaning two, and metallic obviously meaning metal, so there are two metals in this strip, it's a bimetallic strip. When you provide heat, both of them will expand, but as you know, copper will expand more than iron. But the problem is that they're both joined. So the situation is not going to be like this, that copper is coming out from here, right? And iron is like they will both expand. Copper will expand more than iron. But the problem is that they've been riveted. They've been joined together, right? And so what you will notice is that the bimetallic strip will bend. Because copper needs space to flow
But
around.
why would the copper expand more than iron?
Beta, I just explained that. Was the explanation not clear over here?
Was
Was the earlier explanation clear?
Yeah.
Aram?
yeah,
Well, that's the same thing that's happening over here.
yeah.
Okay? But because this time they're not separate pieces of the metal, but they're joined together. And so when there's heat and they expand, the strip will bend. Right? And so when you measure this length, you will see copper is expanding more. Iron has also expanded, but it's expanded less. Right? So iron, less expansion, and copper, more expansion. And right, the one that is expanding more will curve and will cause the strip to curve with it. So right? Bimetallic strips have different applications depending on where they are being used. So I'll take you to the book because they've got better explanations, better illustrations as compared to, right, myself. So here you can see, right, again, bimetallic strip, right, copper and iron, and when it heats, the copper expands more, so that's causing the bend. Now, the way you will place it in different devices depends on how you want to use it. So this is an electric bell, this is a fire alarm, right? This is a circuit. Now, we haven't done circuits, but just, if this contact connects, it will cause the electric bell to ring. When would you want the electric bell to ring? It's a fire alarm, so you would want it to ring when there is a fire, right? So when there is a fire, heat will obviously reach the fire alarm as well. That heat will cause this bimetallic strip to expand. Remember that this brown strip is copper, the gray one is iron. Copper expands more than iron. So what will happen is that this will curve upwards. It will touch the contact, completing the circuit, and the electric bell will start to ring, telling you, oh, right, there's a problem, right, there's a fire somewhere. In, a thermostat, for example, for an iron or any other device which you use for heating, in this case, right, the contact is already made over here, and your iron is getting hot and you're ironing your clothes. As the iron gets hot and it reaches the temperature that you want, right? So what is this? This is the control knob, right? So this is how hot you want the iron to be. Okay. And so the hotter you want it to be, the further away this control knob would be. When it gets hot enough, right? In this case, the copper is on top. So when it gets hot, it will bend downwards and it will break the contact. It will not make the, right, over here the contact was being made and the bell was going off. Over here the iron is heating. When it reaches the temperature that you want, the strip will bend down, it will break the contact and stop the heating, right? And when the iron loses enough heat because you're using it, it will cool, the strip will become straight again, it will touch the contact again, it will start the heating again. Clear?
Yes, sir.
Yeah.
Sure, Param?
Yes.
Okay, so that was for fire alarms and thermostats, and all that is given in the text. So I'm not going to go over that on the whiteboard. So, right, I'll move on to the next bit. Let me just change screens. Okay, the next bit is precautions against expansion. Right, so what we've talked about right now are uses of expansion, but in some cases, right, expansion can cause damage as well, and so precautions need to be taken to avoid that particular damage. Right, one example of that is, as I mentioned earlier on, in the kinetic particle model, is the railway tracks. You remember?
Yeah.
Right, so instead of having railway tracks that are one complete like long piece of iron, or they're joined, touching each other, and so when they would expand, what would happen is that they would break. And obviously, that would be a problem for the train, right? It could cause accidents. And so the way some of them were designed is either just leaving a straightforward gap in the design for them to expand, or right, minimizing the gap by making them tapered. Right, so they're as close as possible, but they're tapered. So this way, when they expand, right, so there's not so much gap over here in total. There's no like empty space as compared over here, but there's enough room for them to expand. And when they expand, they might touch each other, sorry, but they won't bend or break. And right, they also mentioned that nowadays there's even better, uh, design where right, they're concrete sleepers which can withstand large forces, and so that gap doesn't need to be given. Right, then they also give the example of hot water pipes. Right, and right, so those are made of copper, and there's joints left in between for the copper to expand. Right, nothing very technical, so you can read that from the book. Anything else? Not really. Okay, any questions so far?
No.
Okay, next up is the right anomalous behavior of water, or the unusual expansion of water. This is in the IGCSE syllabus. It is given in the O level textbook, but as a going further topic, so it's not part of the syllabus. Unusual expansion of water. So what happens with water, what you would expect with any liquid, is right, when a liquid is cooled, it is obviously losing heat. Losing heat, and therefore losing energy, and so the particles are coming closer together, and so the volume decreases, and when the volume is decreasing, the mass is the same, right? The density increases, right? And so for the same substance of same mass, right? For a solid, the volume is less than a liquid, but its density is higher than a liquid. Make sense?
Yes.
Yeah.
The problem with water, right? The odd thing about water is when it starts to cool, When it starts to when water cools at about 4 degrees centigrade, it reaches its minimum volume and obviously that would mean maximum density. When it is cooled further to zero, between 4 degrees centigrade and 0 degrees centigrade, right, further cooling, water expands. And so, right, for the same mass of water, right, between, right, so 0 degrees centigrade is ice and 4 degrees centigrade is very cool water. And so, right, the volume of ice is actually higher than water at 4 degrees centigrade. And the density of ice is actually less than water. Right? And that is why,
Okay.
right? That is why ice floats on water.
Okay. Yes.
And so they've given a comparison that, right, 100 ml, 100 centimeter cube of water, when it freezes, its volume increases and it becomes 109 centimeter cube of ice. So that's a 9% increase in volume.
Yeah.
Which is a lot. Now, in nature, right, this plays an important role. Why does it play an important role? Because when, right, in winter, right, lakes and rivers and ponds, right, so natural bodies of water, they freeze. And so there's a layer of ice on top. So what happens is when the temperature starts getting cool, the top layer, when it's at 4 degrees centigrade, right, it has maximum density. The top layer of water sinks to the bottom. And warmer water rises to the top. And that repeats. That warm water goes till 4 degrees centigrade, sinks to the bottom. Whatever warmer water is at the bottom goes to the top until all the water is at 4 degrees centigrade. Okay? Then, when the temperature drops further, right, water is actually expanding, the volume's increasing. The volume's increasing and the density is dropping. Which means that the top layer now below, right, below 4 degrees centigrade, only the top layer will freeze. And it will stay at the top because ice is less dense. And what that does is it insulates, right, water underneath. So inside, under the ice is at 0 degrees centigrade. And then you've got the topmost layer of water, which is at 1, and then 2, and then 3, and then 4 degrees centigrade. Right? And so the lower layers are actually warmer because 4 degrees centigrade is warmer than 0 degrees centigrade. Right? Even though comparatively they're all cold for us, but still. And so the warmer layers of water are actually, the lower layers are warmer. And this allows aquatic life to survive during winter when the surface is frozen. Does this make sense?
Yes.
Now, obviously, right, the kind of
Yes.
aquatic life we're talking about has adaptations to be able to survive as cold as 4 degrees centigrade or whatever. So they will have, layers of fat and thick skin and etc. etc. But the point is that, in a natural system, this anomalous behavior of water helps in these situations. All right. Now, as far as construction is concerned, when we humans are dealing with water in cold temperatures, right, allowances need to be made. Just like with expansion, right, the metal pipes and the railways were expanding, and so you had to leave gaps and everything, right? Same is for water. So if you've got water pipes, in very cold, freezing temperatures, and so you need to take care because that the water, if the water freezes in those pipes, the pipes will burst because it's expanding, right? The volume is increasing, so the water is actually expanding. And so the pipe or whatever system it is might break, it might burst. Nowadays, of course, in the drinking system or the water system, in such areas they add chemicals, antifreeze, that actually lower the freezing point further, so they're not freezing at the temperature of the environment. They need to be much lower to actually freeze, right? But other than that, care needs to be taken. And I believe, right, I will stop there. Any questions?
No.
I'll stop there. There's a minor topic of liquid and glass thermometer. You can read it. I will just briefly go over that in the next class. It's a very small subtopic. And then we'll move on to talking about specific classes. In fact, just give me 2 minutes. How long they for all of this? liquid in glass thermometers, right? So you've got a small volume of liquid, in a fine glass capillary, right? And it has markings for temperature depending on the kind of thermometer using, normally going from 0 degrees to, depending, right, might be 100 degrees, might be less, right? It might even be lower than 0. So again, depending on what kind of thermometer you're using, there are two main types. You've got mercury, so that is a liquid metal, and it is useful in, because it has a freezing point of minus 39 degrees centigrade and, right, a boiling point of 357 degrees centigrade. Right, but the problem is that it's toxic. A different alloy is used nowadays, right, which is called Galenstan. It's an alloy which is a mixture of a metal and maybe a non-metal or two metals, and it has a melting point of minus 19 degrees centigrade and a boiling point of 1300 degrees centigrade. Then you got alcohol, which has a freezing point of minus 115 degrees centigrade and a boiling point of 78 degrees centigrade. So again, if you want to go for something hot, you're measuring something hot, this is what you want to use. If you want to go for something cold, alcohol is, right, preferable. It can't go as high because it will boil, but it can go much lower, right? And the whole point is that whatever you're placing it in water, you're using a thermometer to check your fever, right? Heat is absorbed, and that causes expansion. And so the level of the liquid rises, and that gives an indication of temperature. Obviously, these guys need to be calibrated for the temperature readings, but how that is done is, right, it's given in the book. It's not part of the syllabus. I won't be going over it. So if you want to, you can read it on your own. And that's it. So the next class, we will be beginning a new topic. Any questions?
No.
Aram, you okay?
Yes.
I hope
Yes.
you haven't fainted. No? I feel like fainting now. Okay. So I'll see you guys next time.
Okay. Allah Hafiz.
Allah.